In this video, we will look at objects in orbit and work out how we can calculate the speed and distances of orbiting bodies. This is to extend our thinking away from the Earth to bodies like satellites and planets which are in orbit. We have seen already how we can consider objects moving close to the Earth's surface under gravity. In those cases, we consider gravity being constant and also acting straight downwards. And because the object is moving or being thrown over a short distance, we can ignore the curvature of the Earth and regard the ground as essentially being flat. Under these assumptions, we can then work out some equations of motion which allow us to calculate the trajectory of the object. So if we throw a ball at an initial velocity u, it will travel in an arc and fall at some distance x, and we can calculate the distance from our equation of motion. Now we want to expand this idea and work out how things like satellites would move in orbit around the Earth. This would also apply to anything that was in orbit around another body, so how the Moon orbits the Earth and how the planets orbit the Sun. So let us zoom out a bit and see what throwing a ball might look like. This is just a conceptual picture to show an idea. This is not how we work out our equations of motion in space, because in this illustration the Earth is obviously curved. So this is not like the case of a ball being thrown a short distance over flat ground with gravity acting downwards. But this conceptual view allows us to gain a visual understanding about how to think about orbits. So here we are throwing a ball at some initial velocity u, and it falls to the ground a short distance away. If we were to increase the velocity a little bit, then the object would travel a bit further before hitting the ground. And if we increase the velocity a bit more, then the object falls even further away. If we keep extending this analogy, then we can imagine we reach a velocity where the object falls in a way where its curvature of descent matches the curvature of the Earth. And in that case, the ball would be able to go round the Earth and return to its starting point. It would not hit the ground, and this is what we mean by being in orbit, that the path of the object continually retraces. In this conceptual view of an orbit, it can be said that the object is continually falling towards Earth, but continually missing. This is a very imprecise way of saying things, but it hopefully gives an idea of how we can think about something being in orbit. The body continually falls to Earth, but the Earth's curvature falls away at the same rate. So the object never actually hits the ground. And if something is in orbit, then its initial velocity is the same as its velocity at any other point in its orbit. So we can just say that the special velocity for an object in orbit is just v. The velocity v is what we will refer to when talking about orbital velocity. Now, we want to work out what this orbital velocity is. That is, how fast do we need to throw something if we want it to go into orbit? But we note that we no longer have the simple situation we had before near the ground. We are not throwing the object a short distance, gravity is not pointing straight downwards, and in fact, the direction which gravity is pointing is now continually changing. So for these reasons, we cannot now use the Suvat equations to work out the orbital velocity. We will have to do something else, and this is what we will now look at. When we have a body in orbit, then its velocity is constantly changing because its direction of motion is constantly changing. But according to Newton's first law, the object just wants to keep moving in a straight line. So there must be a force which is acting on the body to keep changing its velocity and constantly pulling it inwards. So the result is that the object cannot travel in a straight line and its path keeps continually curving inwards and this is what we call its orbit. If we could magically turn off the force, then the body would just move in a straight line along the direction of the velocity. But because the force is always there, the object keeps curving along its orbit. We know that acceleration is a change in velocity with time, so the body in orbit is undergoing an acceleration because it's constantly changing velocity. And this acceleration is commonly known as centripetal acceleration. According to Newton's second law, F equals ma, there must be a force associated with this centripetal acceleration, and this force is called, not surprisingly, the centripetal force, and we can call it Fc. We will now work out an expression for the centripetal force for a body in orbit. Let us take the case of a body in orbit, and in this example we will assume it's the International Space Station, the ISS. Let's assume the ISS has a mass m and is orbiting the Earth in a circular orbit at a distance r. We've just seen that there is a centripetal force, Fc, which will be acting on the ISS, and Fc is directed towards the centre of the Earth. Now, let's say there are 2 points along the orbit, and the orbital distance between them is ds. We can draw a triangle where 2 sides are the orbital distance r, and the straight line distance between the 2 points is a small distance, which we can call dr. And we can say the velocity of the ISS is v1 at the first point and v2 at the second point. In the following discussion, we are going to consider the case of a very short distance along the orbit, and we call this distance ds. And we will also look at a very short interval of time, which we will call dt. Now, looking at these 2 points along the orbit, we can say that the angle between the 2 points to the centre of the Earth is theta. Now, if we make the 2 points to be very close together, so the distance ds goes towards 0, then the angle theta will also tend towards 0. And in that case, as theta goes to 0, the distances dr and ds become equal. And so we can use ds instead of dr because dr and ds will be the same. If we now look at the velocity vectors and add them together in the way we add and subtract vectors, then we can call dv the difference in the velocities. And because we know that the speed of the ISS is constant and it is just the direction which is changing, we can also say that the magnitude of the velocities v1 and v2 will be the same. So we can simply replace v1 and v2 with v. So now we have 2 triangles which are similar, each having 2 sides which are equal. We have the white triangle with r being the 2 sides, and we have the yellow triangle where 2 sides are v. Hence, we can use the property of similar triangles to write this equation, ds over r equals dv over v. And we can then rearrange this to give an expression for dv. We are looking at a very small interval of time, dt. So if we divide both sides by dt, we get this relationship. In this equation, we can see that we have dv by dt on the left, and we know this equals acceleration. We also have ds by dt on the right, and we know this equals velocity. So we can write a new expression as a equals v squared over r. And this is the acceleration of the ISS in its orbit. This is what we call the centripetal acceleration. We know from Newton's second law that F equals ma, so finally we can get an expression for the centripetal force Fc. This centripetal force always points towards the centre of the Earth, and it's this force which keeps the ISS moving in a circular motion along its orbit. Now, the centripetal force must be the same as the gravitational force from Newton's universal law of gravitation, because otherwise the ISS would not stay in a stable circular orbit. Hence, we can write these two equations of force as being equal. And from this, we can then derive an expression for the speed, v, of the ISS. The main thing to note from this expression is that the speed does not depend on the actual mass of the orbiting body. It is only a function of the distance of the body from whatever it is that it's orbiting. And we can see that the speed of the orbiting body is actually inversely proportional to the square root of the orbital distance r. This is a very important result. It says that a body will orbit at a distance r with a circular speed v, irrespective of its own mass. So it could be a tennis ball, an astronaut, the ISS, or the moon. As long as it has velocity v, then all objects will orbit at a distance r. If we input the actual values for the universal gravitational constant g, the mass of the Earth m, and the orbital distance r of the ISS, then we can calculate the speed of the ISS when it's in orbit, and this turns out to be about 7.7 kilometers per second. So it is actually moving really quickly. Now, if the ISS is orbiting at a distance r from the center of the Earth, then the length of one orbit is simply the circumference of a circle with radius r, that is 2 pi r. So knowing the speed allows us to calculate how long it takes for the ISS to complete one orbit around the Earth. We know that speed is distance divided by time, so we can work out the time for one orbit as being the orbital distance, 2 pi r, divided by the orbital speed. And this time works out to be just over 90 minutes. If the sky is clear, then you can see the ISS with the naked eye as it goes overhead. NASA has a very helpful website and app called Spot the Station, which will tell you when the ISS will go over your own location. And when it does, you will see a very bright object moving quite quickly, typically taking a few minutes to cross the sky. And if you're lucky and it's still clear skies in about 90 minutes time, then the ISS will be back, albeit it'll be slightly shifted in the sky because in the intervening 90 minutes, the Earth will have rotated a little bit on its axis. So this is our expression for the speed of an orbiting object around a body of mass m at a distance r. Since the speed of the body in orbit does not actually depend on the mass of the body, this means that whatever object we have, we just need to make sure we use the expression to calculate the right speed for the distance r we want for the orbit. And if we then give the object that speed, then it will orbit at a distance r. If we assume that there is no other force slowing down the object, then the object will remain orbiting forever at speed v and distance r. This is usually the case for deep space where we don't have any drag forces slowing down the orbital speeds. So the planets have been in stable orbits around the Sun for over 4 billion years, and they will remain like that for another few billion years, until the time, that is, when the Sun becomes really old and expands into a red giant star and its gravity becomes weaker as a result. Then the orbits of all the planets will change, but that is not something that we need to worry about. That is over 4 billion years away yet. Sometimes another body may interfere with bodies in orbit, where the gravitational force from one body alters the orbit of another body, but this is not a common occurrence in the solar system. But when it does happen, say a large comet comes into the solar system, then we can still use our known laws of gravity and orbital motion to work out what then happens to the orbits. In the case of near-Earth orbit, say for satellites or the ISS, then even at a few hundred kilometers above the Earth, there is still a trace of atmosphere which acts over time to cause orbital speeds to slow down, albeit in a very small way. So if we left the orbiting bodies as they were, then over time the very small drag from the atmosphere would slow down the speed of the bodies, and hence their orbital distance r would be changed. We don't want this really, because we want to maintain a constant stable orbit. And this is why the ISS and other large satellites have small booster rockets. Whenever it's needed, a small burst of energy from the booster rockets can recover the speed of the satellites and thereby allow it to remain at the correct orbital distance r. This is not needed a lot, but it is done whenever a tiny orbital adjustment may be required. Otherwise, once in orbit, we can assume the body will just remain there orbiting by itself. The example of the ISS in orbit has shown us how Newton's laws can be applied to things in space orbiting each other, and how we can work out orbital speeds and times. And these laws also mean that if we know where the object is right now and how it is moving, then we can also use Newton's laws to work out where the object will be at some time in the future. And this is how we calculate where the planets will be at any given time in the future, or when future solar eclipses will occur, for example. NASA currently has plans for another human mission to the moon, like they did with the Apollo missions. This new one is called the Artemis program. And the plan is that there should be a human crew landing on the moon sometime in 2027 to 2028. Before that mission to land on the moon, there will be first an initial mission where the astronauts will go into orbit around the moon before returning to Earth. The majority of the orbital calculations for missions like this, both the fly around and the landing mission, are still done using the laws of motion which we have been looking at, but obviously with a lot more complexity. Relativity theory is also used by NASA, but the fundamental calculations which NASA uses to get astronauts to the moon and back are still those of Newtonian mechanics. Newton's laws of motion are not the most complete description of the universe that we have, as we shall see in other videos on relativity theory. But Newton's laws are still incredibly useful and powerful in what they allow us to do in so many scenarios on Earth and in space. In the next video, we will complete our tour of Newton's world by working out how the planets move around the Sun. But for now, I hope you found this video interesting, and until next time, keep thinking physics.